Griffiths section 2.5.1, Conductor Basics. All right, so far we have only really talked about abstract shapes. They have some charge distributions associated with them, and then we were finding the electric fields or the potentials generated by those charge distributions. We're going to become a little bit more concrete. In this video, we're going to talk specifically about conductors. Okay, so you've probably heard of this word before. Conductors are materials that have basically an infinite supply of freely moving electrons. All right. So these electrons can be kind of paired up with their atom in the material and creating local regions of neutral charge, or they can move wherever they want to create regions of negative charge, and where there are vacancies, there's going to be regions of positive charge. Okay. This is in contrast to something like an insulator, where the electrons are not able to be freed from the atoms. Okay, and there are a couple different rules, and that's what this video is going to cover. So here are the rules for conductors. Okay, so let's first imagine we have some region of space that has some external electric field. Okay, I don't know what's creating this electric field. It exists. And then I'm going to say that I have some conducting material, think about it like a metal, and we put that metal inside of that electric field. That metal will generate charges to set up its own sort of induced electric field. Such that if I were to find the electric field inside of my conductor, I would have to take, the external field minus the internal field, or the induced, and that is 0. All right. So there is no electric field in a conductor. That's rule number 1. Okay. All right, rule number 2 comes directly from rule number 1. So if the electric field inside of my conductor is equal to 0, and I know that Gauss's law tells me that the divergence of my electric field is equal to the charge density over epsilon naught. Well, the divergence of 0 is 0. Therefore, the charge density inside my conductor is 0. There's no net charge, right? There's going to be electrons and atoms in there, but there will never be a net charge inside. Okay. So number 3 is a direct consequence of number 2. If the charge density inside my conductor is always 0, but somehow charges are being generated to make sure that I have no electric field in my conductor, then all of the charges that exist are on the surface. All right. 4 comes from rule number 2 still. Remember how we define our potential difference between 2 points? V of B minus V of A is equal to negative E dot dl from A to B. So let's imagine we start at some point in space in our conductor. I end at another point in space, call that A and B. The electric field at each of those points is 0, right? So whatever path I take, E dot dl, still 0 times whatever, that is equal to 0. Therefore, the potential at point A is equal to the potential at point B. Or the potential everywhere inside the conductor is constant. All right. Number 5. There is no electric field inside, right? We already discussed that. But if I look at the edge of my conductor on the outside, the outside electric field is always perpendicular to the surface. Right. I find my surface of my conductor, whatever my electric field looks like, it always is perpendicular to that surface, regardless of the configuration that I put my conductor in. And the reason for this is that the electric field, if it had parallel components, it would be able to then push around those charges, and those charges would eventually generate this condition again. Right? So I can imagine changing the conditions, change the electric field, moves a current around on the surface then make sure that this is always true. All right, those are the 5 rules for conductors.